Hi everyone, today we're going to talk about calculating pH of weak acid solutions. This is tied to Learning Objective 6.12 that students can reason about distinction between strong and weak acid solutions with similar pH, including percent ionization, concentration needed to achieve the same pH, and amount of base needed to reach the equivalence point. How do you calculate pH of a weak acid? First, you start off by writing the net ionic equation. Then you determine the equilibrium expression Ka. Now then we develop an ice table, and we use Ka, an initial concentration of the weak acid, to find hydrogen ion concentration and the pH. And finally, we should do a percent check to see if it is within the 5% rule. If we drop the X, the change in concentration, considering it to be small and negligible. Find the pH and percent dissociation of 0.1 molar acetic acid with Ka of 1.8 times 10 to the minus 5. What are the major species? So first we write the net ion equation, acetic acid ionized into hydrogen ion and acetic ion. Then we write the K expression of product over reactant concentrations. Now then we set up a nice table. We start out with 0.1 molar of the acetic acid and nothing of the hydrogen ion or the acetic ion. Now we let X be the change in molarity. So we subtract X from the acetic acid. We add X and X to the hydrogen ion and the acetic ion. Now at equilibrium, we have 0.1 minus X, X and X. Now we set up the Ka expression using the numerical value of 1.8 times 10 to the minus 5 equal to product concentration X squared over the reactant 0.1 minus X. Now look at the X in blue color. We assume it to be small and negligible compared to the original concentrations. Therefore, we're going to drop it from the equation. And we solve for X, which is determined to be 1.3 times 10 to the minus 3 molar, and pH therefore is 2.89. Then we do the percent ionization check, which is equal to the hydrogen ion over the original weak acid concentration times 100. And we now have 1.3%, which is less than 5%, and we say the assumption is valid that we could drop the X from the calculations. And the major species present are the acetic acid molecule and water. We have very few ions floating around at equilibrium. If we dilute the solution of the acetic acid by tenfold, how would that affect the pH and the percent dissociation? So here we are, we're going through the same kind of calculation as in the last question, except we replace the 0.1 by the 0.01, and then when we calculate the X, hydrogen ion concentration is 4.2 times 10 to the minus 4 molar, and the pH is 3.38. And the percent ionization check now is becoming 4.2%. 4.2 times 10 to the minus 4 over 0.01 molar times 100. Major species are still acetic acid and water. Now, let's compare the two kind of acetic acid, 0.1 and 0.01 molar. We find the pH is increasing from 2.89 to 3.38, while the percent ionization is increasing from 1.3 to 4.2%. Let's see if it makes sense. First of all, when the weak acid is diluted by 10 times, the pH will increase because the hydrogen ion concentration decreases when more water is added, resulting in a less acidic solution, therefore a higher pH. Now let's look at the percent ionization. Why does it increase? Here we are disturbing the equilibrium when we dilute it, so therefore we are going to calculate quotient. When other species are diluted by 10 times, we divide their concentration at equilibrium by 10, and that will factor into quotient is 1/10 of Ka value. Note that. So when quotient is less than the Ka value, that means the reaction has not yet reached equilibrium. It will still go forward to the right to achieve equilibrium, therefore increasing the percent ionization. If we have the same pH of a strong and a weak acid, then What about the concentration? Well, at the same pH of 2.89, strong acid HCl dissociates completely to form the hydrogen ion. Therefore, the hydrogen ion concentration is 10 to the negative 2.89, which is 1.3 times 10 to the minus 3 molar, which is the concentration of the weak acid before dissociation. However, with a 0.1 molar weak acid, acetic acid, they only ionize partially. Therefore, it has many unionized acid molecules present. And in order to achieve the same pH, the weak acid must be in a much higher concentration than the strong acid. So this is something to be noted. If they have the same pH, the weak acid would have a higher molarity. Now, when we compare same molarity of the strong and weak acid, they have the same initial concentration. Again, hydrochloric acid, strong acid ionizes 100%. The weak acid ionizes partially. Therefore, the hydrogen ion concentration in HCl would be greater than the hydrogen ion concentration in acetic acid. Therefore, the pH of HCl would be less than the pH of weak acid. So this is another point to be noted. Of equal molarity, the pH would be lower in the strong acid than the weak one. What about if we neutralize equal molar and equal volume of the strong and weak acid with the same kind of NaOH? Will the volume to reach the equivalence point be different? Okay, so first of all, we write the overall molecular equation for the strong acid, strong base neutralization, and we write the net ionic equation, which is H plus and OH minus to form water. However, when we write that for the weak acid neutralization, it's a bit different because the weak acid molecule does not dissociate. So the net ionic is acetic acid plus hydroxide ion to make water and the acetate ion. So note the differences between the two net ionic equations. Now, if we then use 0.1 molar, 20 milliliter of each of the acid to be neutralized by 0.1 molar NaOH, we use the MAVA is equal to MBVB equation. And naturally, the volume of NaOH is to be the same for both kinds of neutralization, 20 milliliter. That may come as a surprise to some of us. Well, because the hydroxide ion is such a strong base that it can completely withdraw all the hydrogen ion hidden in the strong acid and the weak acid molecule. And this is something to be noted. This is not ionization of the strong or weak acid. It is neutralization. So remember, hydroxide ion is so strong, it's going to take away all the hydrogen ion, whether strong or weak acid. So comparing, the nature of the acid, HCl strong, acetic acid weak. They have same molar, same volume. Percent ionization, HCl is 100%, acetic acid partially. Hydrogen ion concentration, HCl will be 0.1 molar because it ionizes completely, whereas for the acetic acid is 1.3 times 10 to the minus 3 molar, calculated from Ka and the ice table. For the pH, strong acid HCl has 1.0, whereas the weak acid has 2.89. For the volume of NaOH to neutralize, they would use the same amount, 20 milliliter each. Practice problem number 1. Calculate Ka from pH. 1.10 molar formic acid has a pH of 2.38 at room temperature. Find Ka and percent ionization. So from the pH, we can then determine the hydrogen ion concentration to be 4.2 times 10 to the minus 3 molar. Now we write the equation for the ionization of formic acid to form formate ion and hydrogen ion. Now we set up the ice table, and at the bottom line at equilibrium, for the formic acid, we have 0.1 minus 4.2 times 10 to the minus 3, whereas for the formate and hydrogen ion, they have the same concentration of 4.2 times 10 to the minus 3. Now we can then plug it into the equilibrium Ka expression, and we calculate Ka to be 1.8 times 10 to the negative 4. Percent ionization check is the hydrogen ion over original concentration of 0.1 times 100. We have 4.2% ionization. Therefore, the assumption to drop the X is negligible, is acceptable, is valid. For practice problem number 2, Determine the pH from percent ionization in a 1 molar cyanic acid, HCNO, dissociation 0.59%. Determine the pH and Ka. So this time, we go from the percent ionization to figure out the concentration of the hydrogen ion in the original 1 molar solution. That's determined to be 5.9 times 10 to the minus 3 molar. Therefore, the pH based on that is 2.23. And now we write the ionization of this cyanic acid. And then at equilibrium, we document their concentration. For the cyanic acid, it is 1 minus 5.9 times 10 to the minus 3. For the hydrogen ion and the CNO minus ion, they have 5.9 times 10 to the minus 3. Now, therefore, we can calculate the Ka, which is 3.5 times 10 to the minus 5. For practice problem number 3, now we have a mixture of weak acids. Supposedly, we have HCN 1 molar and 5 molar HNO2, each one with different kind of Ka value. What will be the pH of the resulting mixture? Because HNO2 is a stronger acid than HCN because it has a larger Ka, we'll now dissociate the HNO2 first. Using X being the change, starting with 1 molar, we can calculate the Ka value to be 4.0 times 10 to the minus 4, and then the X, which is the hydrogen ion concentration, 2.0 times 10 to the minus 2 molar. So remember, this is the hydrogen ion concentration from the stronger of the 2 weak acids from HNO2, 2.0 times 10 to the minus 2 molar. Now we go to the second part, dissociation of the HCN, and then we set up the equilibrium concentration. Let Y be the change, starting off with 5 molar. Now what I need to point out is regarding the hydrogen ion concentration. We not only get Y being the change, we also get a carry down from the first weak acid hydrogen ion on 2 times 10 to the negative 2. It is really important that we account for it. Now we use Ka of 6.2 times 10 to the minus 10, and we set it up a product over reactant concentration. The Y is very small because the Ka is 10 to the minus 10. Therefore, we drop the Y from the expression, and we calculate Cn minus to be 1.6 times 10 to negative 7 molar. Now, the total hydrogen ion concentration from the two parts is 2.0 times 10 to the minus 2 from HNO2, and the 1.6 times 10 to the minus 5 from the HCN. But notice the second portion is so small compared to the first part, we can drop it. So overall hydrogen ion is 2.0 times 10 to the minus 2 molar, pH is 1.70. The conclusion is that when you have a mixture of 2 weak acids, the acid with a larger Ka value will determine the pH. Practice problem number 4. Now we have a strong and weak acid in the mixture, such as HCl 1 molar and also 1 molar acetic acid with a Ka value. What would be the resulting pH? HCl is a strong acid that ionizes completely. Hydrogen ion is 1.0 molar, but with acetic acid, we have to go to equilibrium to solve it. Notice that the hydrogen ion in acetic acid, now we have to add 1.0 molar to it because we got a carry down from the hydrochloric acid in the same beaker. Now using Ka of 1.8 times 10 to the minus 5, we set up the ratio and drop the X from the expression because 10 to the minus 5 is relatively small dissociation. And so now the hydrogen ion concentration is actually 1.8 times 10 to the minus 5 molar. If we add up the total hydrogen ion concentration, it's 1 plus 1.8 times 10 to the minus 5, which is negligible compared to 1. Therefore, the pH is 0. The conclusion is that when you have a mixture of strong and weak acid, that the strong acid is going to determine the pH of the mixture. To summarize our learning today, students have learned 1, the distinction between strong and weak acid with similar pH, including the percent ionization, the concentration needed to achieve the same pH, and the amount of base needed to reach the equivalence point in a titration. And furthermore, we learn how to calculate pH and Ka values of weak acids, or in a mixture of 2 weak acids, or in a mixture of a strong and a weak acid. I hope that you have found the video helpful to you. From the team of MLCA, we'd like to thank you for watching our video and hope to see you again soon.